Okay, another example now. Bob takes a kettle off the stove and it cools down so that after 5 minutes, the temperature of the kettle is 70 degrees. The room has a temperature of 20 degrees. Now think about why they have told us that. Imagine if you've got something that's very hot and it's cooling down. Will it cool down more quickly if you've put it, in a really icy environment, or will it cool down more quickly if it's in a hot environment? It will matter, won't it? So you can see that the rate of cooling here is going to be dependent on how hot the kettle is compared to the room. Okay, so we need to show that T equals 20 plus 80 e to the minus kt satisfies this cooling equation. Now a cooling equation is by its very nature a rate of change, because it's the rate of something cooling, it's the change in temperature. dt, now you have to be careful in these sorts of questions where you've got big T and little t. Big T is the temperature, little t is always time. So dt is equal to negative k big T minus 20. So we need to show that this will satisfy this. That's very similar to what we did in the last example, and show it gives the correct temperature of boiling water as 100 degrees. In other words, when little t equals 0, or at the start of the experiment, we're expecting big T should actually be 100. Okay, so first things first, let's start by showing that this satisfies this. So let's say that the left-hand side is dt, and then we can find what dt is by just differentiating this. We'll ignore the 20, we'll bring the negative k out the front here, and then multiply it by the 80 e to the minus kt, and then we can say the right hand side is equal to minus k t minus 20, and subbing in big T there, which is 20 plus 80 e to the minus kt minus 20. We can see that the 20 and the minus 20 are going to cancel each other out, so we're going to just have minus k multiplied by 80 e to the minus kt, and that is equal to the left-hand side. So a few ways to set that out, but whatever makes the most sense to you. I think starting with this and then finishing with that, and then you can say right-hand side equals left-hand side, or you can just finish with the left-hand side, because there it's obvious. We've got an in and an out. So we've shown that our T satisfies this differential equation, but now we need to prove that it gives the correct temperature of the boiling water. So I would set that out by just saying when little t equals 0, big T is equal to 20 plus 80 e to the 0, and e to the power of 0 is just 1, and 20 plus 80 equals 100. So that way we've shown that initially the kettle was 100 degrees. Now for part B, we need to find K. So let's start with the original equation that we were given and look for a clue. We know that when T equals 5, temperature was 70. So you can write down what you're doing there. Let T equal 5 and big T equals 70. And now we can clearly see what we're trying to do, so that in case we mess it up, we're going to get marks for the correct thinking perhaps. So 70 equals 20 plus 80 e to the minus 5k, subbing T in as 5 there. So let's get this a bit simpler. Let's subtract 20 from both sides. Now let's get rid of the 80 by dividing both sides by 80. So I'm going to have 5/8 over here is equal to e to the minus 5k. And just leaving it like that is quite straightforward. You could have it as a decimal, 0.625. Now I've got it in 3 bits. Something to the power of something equals something. So I can rewrite it as a log. E to the power of minus 5k is equal to, and I could put 5/8 here. I might actually write it as a decimal just because it fits more neatly on one line. So now to find k, I need to divide both sides by -5. So always include this last line rather than reaching straight for your calculator. We've got the natural log of 5/8, which you can write that way if you like, over minus 5, and k works out to be 0.094 to 3 decimal places, and I'm storing that in my calculator so that I can use it later. Okay, so for part C, how long does it take the kettle to reach 25 degrees? Let's do that part over here. So we want to let T equal 25 and find little t. Now, you don't don't need to write that at the start, but it's quite handy just to give yourself a bit of direction so you know what to do. So let's fill this in now. We've got 25 is equal to 20 plus 80 e to the minus kt, where we know what k is already. We've found that. Now, there's no need to write in minus 0.094 t, because then you're tempted to use a rounding off of it later. We want to use the exact value, and the quickest way to write this thing is just to write k. And then when you need to use it, you can just put k in. Now, if you're concerned that an examiner is not going to know if you know what k is, here I would just put stored as a. So you remember what it is, and anyone reading your work knows that you know what it is. Okay, let's subtract 20 from both sides. Now let's get rid of that 80 by dividing both sides by 80. So we've got 5 divided by 80, which is 1/16. Now we've got it in 3 parts. Something to the power of something equals something. So we can write it as a log. E to the power of minus kt is equal to 1/16. And so to get the t by itself, I'm just going to keep working up here because I'm running out of space. T is equal to the natural log of 1/16 divided by a negative k, where I know what that is. So now in my calculator, negative log of 1/16 divided by negative, and I put in my negative a there. And I get 29.495. Okay, and that goes on and on. Always read back and think, what's my question asking? This is in terms of minutes, isn't it? So how long does it take? It takes 29.5 minutes. Now, if I was looking for a whole number answer, I couldn't round it down to 29, even though this technically does round down. Because after 29 minutes, my kettle won't be down to 25 degrees yet. If I need a whole number of minutes, I'd actually need to wait for 30 minutes to be sure it's down below that temperature. Does that make sense? So have a look if the question's asked you to round it. This one actually hasn't specified, so I'd just leave it like that and say minutes to 3 decimal place. It's a bit funny to round minutes off as decimals though, isn't it? To me, if this is minutes, we should really change it to minutes and seconds. And if I hit that minutes and seconds button there, I get 29 minutes and 29 seconds and 43 point something. So it's really closest to 29 minutes, 30 seconds. That might be a better answer. 29 minutes, 30 seconds. And then I can write to the nearest second, which I think is a nicer way to measure that. Okay, the last step now is that we have to graph this. Now, quick inspection of it, I can see that we have, like our last example, we've got a transformation here. We've got negative kt. So a basic exponential curve looks like this, doesn't it? And if we've got a negative kt, then we've actually got decay, and it looks more like this. It's some rate that's going down, and that makes sense to our story. We've got a temperature that's very high, and that's dropping. We can also see that our graph's been lifted up 20, so it's come up like this. And we know some information already. When t was 0, the kettle was 100 degrees, right? So we know that we're starting from 100 degrees or so. So all we really need to consider when we're doing our little mud map sketches is the basic shape of the curve that we're looking for. And we know that we've got decay. It's going to go down. So starting off, label your axes. We've got big T and little t, and we're starting at 100 degrees. And then it's dropping off like this. And at some point, it's going to stop dropping off. As t gets really, really big and just goes on indefinitely, what's going to happen? Well, we're going to have e to the power of a negative, really large number, aren't we? So e to the power of a negative large number, I mean, let's just think about what it would be if it was negative infinity. Isn't that the same as 1 over e to the power of infinity? Now that's as good as 0, isn't it? Because the bigger this number on the bottom of a fraction gets, the tinier this number gets. It becomes almost nothing. So if we've got 20 plus virtually nothing, we can see that we're approaching 20 degrees. It's approaching the temperature of the room, and that makes complete sense. So that tells us that we're approaching an asymptote, but never quite reaching it, of 20 degrees. The only other thing you could add is putting in a point that you know for scale. So you could put in the point 5, 70, because we know that after 5 minutes, we're at 70 degrees.